So before starting the next talk, Laura would like to add a few words to her talk.
Yes, thank you. For an involuntary omission, I forgot to tell that the co-authors of the things that I talk about of this geometric interpretation are Jessica Jaures and Sergei Voronin. Thank you very much, and sorry.
Okay, thank you, Laura. And now it's time to hear our colleague Alain Muniz from Universidade Federal de Pernambuco talking about foliations on complete intersections.
Thank you, Jorge, for the introduction. Thank you all for coming. So these talks will not be as amazing as Laura's, but it's a great pleasure to be here. So I thank you very much. The organizer, sorry. I thank very much the organizers for the invitation. And thank you. So I'm going to talk about foliations on complete intersections. It's a joint work with Christiane Kuster, Matheus Figueira, which is there, and Ruben Zabi, who is teaching now. And let's, our setup is like a codimension 1 foliations on projective varieties, smooth projective varieties. So it's, well, one way to define these are like, you take one form, you take the contraction map, and we have these guys. The tangent sheaf, this is the kernel, the normal bundles, these guys that appear here. And these are integrable one form with singularities in codimension at least 2. Okay, just the setup. I believe everyone here is familiar with these notations. And the problem we are addressing is like to describe the space of foliations with a given normal bundle. So you fix a variety, you fix a normal bundle, you want to describe the space of foliations. So it's this space, you take all the integrable one forms with singularities in codimension at least 2. And well, this is you have a projective space, you have some algebraic equations. This is a quasi-projective algebraic varieties that has several irreducible components. And our goal is to describe these components in some cases. So we further assume that we are in Picard 1. So, and then we write this, take O1 to be the ample generator of the Picard group, and you write this so that it's just a psychological thing for when X, the D here that appears is the degree, is so that if X is the projective space, this agree with Alcides' definition of degree. So, and we have this notation, say fo XD, so codimension 1 foliations with this normal bundle, and we will say that it has degree D, even if the variety is not the projective space. Just okay. And what we know it's like for Pn and well, for P2 there's nothing to do. Like the integrability condition is automatic, and the space is the open subset of the projective space. And for n at least 3, have this in degree 0. This variety is irreducible. Every foliation is given by the fibers of a linear projection to P2. So this is essentially due to Darboux. So if you can read this from the Darboux normal form for differential forms. And for degree 1, we have 2 components. This is the work of Jonulu. And for degree 2, we have 6 components. The work of Alcides Neto and Dominique Cerveau. For degree 3, have a partial classification, at least 24 components, is by Rafael da Costa, Rubem Lizarbe, and Jorge Vitório Pereira. And besides the projected space, we have, in degree 0, we have this work by Benedetti, Faenza, and myself. It's, we describe this. These are cominuscule varieties. These are homogeneous space, and the cominuscule is a representation theoretic definition. And use this, in this paper, we use representation theory to describe these guys. And also, this, in this paper, this first paper, we described this for some of the cominuscule varieties, and later, with Vladimiro, Christiane, we did some computations, and we could like complete the cominuscule case, but it's still in progress, so we didn't write it down properly. And for adjoint varieties, so this, if you know representation theory, if you know representation theory, this means cominuscule case means that the tangent sheaf or the tangent bundle of the variety is associated to a irreducible representation of the group. And the next case, like when the adjoint case, when the tangent bundle is not irreducible but has a filtration of length 1, is the case that was dealt with by Christiane in his thesis. And when the variety has Picard number 1, this, you have this, it's irreducible. Every foliation of degree 0 is given by a pencil of hyperplane sections. And there's some interesting case when the Picard, there's, besides this case, there is the case of Picard rank 2, when there's more foliations. And the case of smooth complete intersections, it appears in a paper by Carolina Araújo, Maurício Correia, and Alex Massarenti. And they prove that these foliations are only pencils of hyperplanes. Hyperplane sections.
What is the definition of 0?
This is here. I'm taking D plus 2 to be the normal. So Picard rank 1, O1 is the generator of the ample generator, and this is just a notation, just psychological. If X is Pn, we have the actual degree. So, but in the other cases, it's just a notation. We defined the degree to be like that. Okay. It's just to keep track that in the case we're interested in, we are going to embed this variety in a projective space and take the O1 to be the pullback of the 1 from the projective space. So that things, the degrees match. Okay? Okay. So how do we describe these spaces? How we pursue this problem, right? How we can like give this variety is a quasi-project variety, has several components, has some, although there are quadratic equations, but there are a lot of them. It's very hard to describe it like in an explicit way. So what we do to describe this variety is to know how their irreducible components behave. So there are several techniques. I just listed like these main things that we are going to use. And first is like the knowledge of types of reducible components that may appear in our cases. So there are plethora of papers describing reducible components of such type. I'm not going to go through that. I'm only going to give you some examples for besides knowing what types irreducible components that we know we have. And there are some structure classification results that we know, in our case, with Fixen, we know what type of components that can appear in our case. So actually, we are not going to use this ability. We are going to use this technique of deformation of rational curves along foliations. That's pioneered by Jorge Vitório Pereira, Frank Torre, and Frédéric Touzé. And we are going to use also the extensions to ambient variety. Say X is, in our case, X is embedded in a projective space. We are going to see if the foliations extend to the ambient projective space, right? So therefore, the first point there, the irreducible components that we know that we are going to use. There's the logarithmic components. So you'll fix some integers, and you'll have one form defined like that for some sections of this OXDI, and some constants that will satisfy this relation. And it's a theorem by Omega Calvandra that if X satisfies this hypothesis, then these guys form irreducible variety that's a component of the space of foliations on X with this degree, the sum of the di's minus 2. Okay, I believe everyone's familiar with this logarithmic foliations. Also, there's the linear pullback foliations. You take a linear projection from, that should be a dashed arrow here. That's a rational map. And you get you take a foliation on P2 of degree D, and take the pullback. So this is a linear pullback, what we call a linear pullback foliation of degree D. So, and result by César Camacho and Alcides Neto is that these guys form an irreducible component of the space of foliations of degree D. This means like if you take a pullback foliation, deform it, it continues to be a pullback foliation. So we also take, if you take this, an embedding of this, of a foliation, some Pn, we can define these guys, the same space, that we take a linear projection from Pn, restrict it to X, and take the pullback of some foliation. And this is not clear whether it's a component. We believe it is, at least for complete intersection, but we didn't prove it, so I'm going to say. In the case we are going to see in a moment, these are the pullback foliations that appear are logarithmic, so we are safe. So they are components because of the logarithmic part. Okay? Okay. Some foliations tangent to algebraic actions. Actually, yeah, we are not going to use that very much, but there's also this construction that you know that some foliations that have that are some C star action that is tangent to the foliation, and on P3, these are. If you take a C star action on P3, you are taking a guy in some Cartan subalgebra or SL4, and these you can write as or GL4 actually, and you can write this the action of a vector field like that. And you can define this space of these forms that are tangent to tangent and invariant with some action of this. Here I'm just sloppy because this means that U is similar to V. So after some linear change of coordinates, this becomes the V ABC. So you take this guy, take the closure inside the space of foliations, and we get some subvariety, and it's a result. Here I'm only put one, but there are some results by Rafael, Ruben, Jorge that with some condition you can prove that this set is a irreducible component of the space of foliations. Okay. So, going back to Pn, we have this for degree 0, we have one component that's logarithmic. It's 1, 1, so it's a pencil of hyperplanes. For degree 1, we have 2. There is one that's logarithmic 1, 2, so it's a pencil of quadrics with one double hyperplane. And also the log 1, 1, 1, that is actually, if you take like this, we have 1, 1, 1, so we have like 3 hyperplanes. So you take this to be x0, x1, x2, and you get like a map to P2. So these are the pullback, linear pullback of degree 1. And in the case of degree 2, we have the 6 components that are like rational, so a pencil of cubics with a triple hyperplane, a pencil of quadrics, a logarithmic with 2 hyperplanes and a quadric, logarithmic 4 hyperplanes, the linear pullback of degree 2, and also these guys that come from a C star action with weights 1, 2, and 3. And the invariant, the semi-invariant form has weight 5. And this guy is actually what is known as the exceptional component. So up to degree 2, with the components that we defined, we get everything. I'm not going to go into the degree 3, but it's we need to define something more, but whatever. Okay, so these are the components we know. So this part is okay. Well, in the literature, there are several more types of components and results and by many people. And I'm sorry to not mention them. And now we go to the structure thing. So if you have, if you're given a form, how do you decide where it fits? So we need some structure theory to go there. And there's this theorem by Loray, Pereira, and Touzé. There's a codimension 1 single foliation Pn of degree 3. Then we have this, either it's defined by a closed rational one form without codimension 1 zeros, so it's morally logarithmic foliation. There is either there exists a subfoliation that's algebraically integrable, so it has a rational first integral of degree 1. So I didn't define higher codimensional foliations, but I hope you don't mind. And so the third item is just that F is a linear pullback of a degree 3 foliation on P2. Or here should be a F, but I didn't catch this error. So F admits a rational first integral. So it's algebraically integrable. If you are given a foliation, how do you use this thing? If you are given any foliation of degree 3, you can search for it must satisfy one of these items. So if you're and hopefully once you have the description. For instance, if it falls in the first one, you know it belongs to a logarithmic component. And just to remark this, in this paper, it's stated for P3, and in later, the statements for Pn, for n at least 3, and they just adapt the proof, and the ideas are essentially here, right? And okay. What we proved, we proved like just straightening a bit what is essentially gathering the arguments that appears on these previous papers. We could like see that well, with a lot of work to get there. What we proved for is this most technical result that says that if you take any smooth project variety that's covered by lines, here covered by lines, I mean that it's embedded in a projective space, and it's covered by true lines of this projective space that have like lines of this projective space that are contained in the variety and cover the whole variety. And if you take a codimension 1 singular holomorphic foliation of degree D and satisfies one of these two conditions, either the degree is 1 or the first class of the tangent sheaf satisfies this inequality. If one of these two hold, we get these three possibilities. So either it's given by a closed rational one form without codimension zeros, or it's algebraically integrable, or it has a subfoliation codimension 2 and degree at least 2 less than D. Okay? So it's have a lot of hypotheses, but let me just give you an idea of how we prove this result. Essentially, what we analyze is the splitting type of the pullback of the tangent sheaf. So we have you take a general free line. A line there is free. It means it's this. Is that the normal bundle of this embedding is globally generated. So it must be, well, it's a line, so it sits inside the normal bundle of the line with respect to Pn, so which just all copies of O1. So it should be something, if it's globally generated, this decomposes as a sum of line bundles. And since it's globally generated, all these summands should be non-negative. And because it's a line, this summand should be at most 1. So you get something like that. It's O1 to some power and O to some power, right? So the normal part of this. And from that, we get this, the pullback of the tangent sheaf of the foliation is also some direct sum of line bundles. And as it should be, like it sits inside this guy, you have some restriction on the degrees. And from the computation, we get this either the degree is 1 or satisfies the inequality, you get this -1 here. If you get this -1 here, what we get is that this pullback has sections. And we can define what's called the tangent foliation. These things like, you have the space of, say, here you have the space of these maps from P1 to X that parameterize a line. You take the variety that parameterizes these maps. And you can see if you, for each point that corresponds a line, you give a subspace that corresponds to this H0 of this guy. These give some, say, tangent directions to the deformation of the line that is, say, we are deforming this line along the directions given by the foliation. So in this situation, we have this. We have a positive dimensional foliation with this F-tongue. I'm not going to the details of how to construct this thing. And what the Loray, Pereira, and Tuzé prove is that they prove a lot of things, but what we are going to use here is this dichotomy. Either this F-tongue is not algebraically closed, algebraically integrable, and F is defined by a closed rational one form without coordination on zeros. This has a lot of, this is not the precise result in their paper, but with the hypothesis we have, this boils down to this statement. And, or the F-tongue is algebraically integrable, and either F is also algebraically integrable, or admits a subfoliation of codimension 2 and degree bounded by this number. Okay? So, minus 2.
But then, if the degree is 1, become minus 1.
If the degree is 1, you don't have this. Or at least, yeah. For the definition of degree we gave, foliation could have negative degree. It's just a thing. But in the, we don't exclude this case. So moving to, this is actually one thing that we need to prove, that going to complete intersections, there are no negative degree foliations. Okay, so now we narrow down the situation to complete intersections. So for a smooth complete intersection, we assume this condition. This condition is equivalent to being covered by lines. You see if the if you have a complete intersection, one can show that if you have a line inside your variety, that the normal bond of this line is globally generated. So if you see that this at least 2, well, it's not that easy to see, I think. If it's covered by lines, then this inequality holds, and the converse is it's a bit tricky. So what we get is that a smooth complete intersection Pn of dimension at least 3, and you suppose that this condition, this inequality holds. Then we have a codimension 1 foliation of degree 1. Now, if we specialize to degree 1, is either defined by a closed rational one form without codimension 1 zeros, or the Misa subfoliation of degree 0. One of the 3 conditions dropped because of this. I'll just show in a moment. And just saying that, recall that we have this equality for hypersurfaces. So we get that this number should be at least 2. So the degree of the hypersurface should be at most n-1. So we have some restriction of what kind of hypersurface that can apply this result. So how do you prove this thing? From the theorem, we have these 3 conditions: closed rational one form, algebraically integrable, or has a subfoliation of degree 2, or codimension 2 and degree at most -2. And this is excluded. We prove that for complete intersections, we cannot have the foliations of negative degree. So d -2 Yeah, I should put here, this is d minus 2 minus 1. So there's nothing of degree is more than 0. So this option is not available. So we have these two, either closed rational form or algebraically integrable. So if it's, in the first case, we are OK. In the second case, if it's algebraically integrable, we have that either this is a thing that you have this pencil of hyperplanes, of hypersurfaces, and you see either you have only irreducible fibers. Hence, this is by Halfing that it appears in a paper by Loray, Perret, that if you have this condition for a complete intersection of dimension at least 3 is automatically simply connected. So we can show that these guys, if there is a rational first integral with only, well, we can show that the first integral has at most 2 multiple fibers, and you can like construct by hand a closed rational one form without condemnation 1 zeros that defines the foliation. So this goes to the first case, or if there is some, actually if there is some fiber that's not irreducible, you can use the component of the fiber to construct a subfoliation of degree 0. So you have this thing. So let me go back to the statement. This, yeah, precisely what we had here. Okay. So we have this. We have our structure theorem. We have the components that we know about, and we can move to what we mean by extending a foliation. So we think of the varieties embedded in some project space and fix this situation so that it's like minimally embedded. So the generator of the Picard group is precisely the pullback of O1 on Pn. And we have a natural map from the forms on Pn to forms on X. You just take the pullback. Just have the inclusion of X in the variety, you take the pullback of the form. And one wonders if this map is injective, surjective, if it preserves the locally decomposable forms, integrable forms. There are various situations when something holds and the other don't, and well, it's a mess in general. So there are several results on these lines, but there are 2 results of what I want to quote. Is that this result by Mateus Figueira. If you take X to be a smooth hypersurface of dimension at least 3 and degree at least 2D plus 1, then every foliation has a unique extension to Pn plus 1. So you take this you look at this map, you need to look the map for 1 forms and the map for 3 forms. That you take omega, wedge d omega, and you see that if the restriction of this guy of omega, wedge d omega is 0, it's because there's some lifting, precisely 1 lifting, that's also integrable upstairs. And one result that we prove is that if you take a smooth complete intersection of type D1 through DS, and dimension at least 4, if the degrees are at least 3, and take any codimension 2 foliation of degree 0, has a unique extension to Pn plus S. This is actually, there's a This is mainly due to Mateus. In his thesis, he proves that if you take a distribution of codimension 2 and degree 0 on X, it leads to a distribution on this projective space. But it's actually, if it's an exercise to see that if you take a locally decomposable, say K for 2, two form, you take a two form of degree 0 on a projective space that's locally decomposable, it must be integrable. It's just an exercise. You just put the equations, you see that if it's locally decomposable, then you can use this, the normal forms in the Ayrton's paper. That's it's Ayrton Medeiros. It's not hard to see that. So Mateus proved that the thing lifts as a distribution, as a locally decomposable form, and we see that it's a foliation. So every codimension 2 foliation on X lifts to a codimension 1 foliation, and the lifting is actually unique. And also, we require, there are some things that I'm particularly not happy with this degree at least 3, but we couldn't improve this. But for what, there's also the result for hypersurfaces. If you take quadric hypersurface, there's a result by Carolina Araújo and Stéphane Troel. This is on fun foliations 2. And when they describe the degree, the foliations on quadrics, this result appears that if you take actually, if they prove like that. If you take a foliation there on degree 0, codimension 2 on the quadric, not only 2, but they prove that it's given by the fibers of a linear, the restriction of a linear projection from the ambient projective space. They prove that. Okay? So, put these pieces together, like, recall that in our structure theorem, one of the options was that the foliation has a sub-foliation of degree 0. But if it's a sub-foliation of codimension 2 and degree 0, as we already shown, this should be like the restriction of some linear projection from the ambient space, projective space. So what we get is like for dimension at least 4, and C1 of Tx at least 2. If either S is a hypersurface, so as a hypersurface of degree at least 2, I'm not counting hyperplanes here. Or the degrees are at least 3, then we get that the space of foliations has these decompositions. It's either given by a pencil of quadrics with a double hyperplane, or a linear pullback of a degree 1 foliations on P2. Here, I don't have the problem of proving that the linear pullback is a component, because in degree 1, linear pullback is the same as the logarithmic 1, 1, 1. So we are fine. So in the proof goes like that, by the structure theorem, either F is logarithmic or has some foliation of degree 0, but some foliation of degree 0 are linear projections. So either F is logarithmic or a linear pullback, which is also logarithmic in degree 1. So that's it. Okay? There is another let me just go back for a second. Here we are using this, this theorem holds for dimension at least 4. So dimension 3, it's we still don't really know how to approach. But for hypersurfaces, we can do a little better. For a smooth hypersurface on PN with dimension at least 3, and it's not a quadric on P4, so not a three-dimensional quadric. So we get that they have the same decomposition. There are only 2 logarithmic components and the same. So how do you prove this result? So that when the dimension is at least 4, we have the previous result for for complete intersections in general, and degree at least 3, so that actually there is some degree at most, like this inequality is inverted. So the previous theorem, we need that C1 of the tangent is at least 2. If the C1 of the tangent is at least 2, we are in dimension at least 4, then we require that the degree of these guys are, sorry, this should be at most 3. And if you take like degree 3 and dimension 3 and degree at least 4, this follows from Mateus' result. So what are we left with? Is just the case of n equal the dimension equals the degree equals 3. So in the dimension at least 4 in every degree, it's okay. The dimension 3 and degree at least 4, it's okay. It remains dimension 3 and degree 3. And this case you can do actually by hand. This is not you have the space of you take a one form on the cubic, on the three-dimensional cubic. This has a lifting to P4 as a one form, so it lifts as a distribution. And you suppose it's not integrable, so you have like omega wedge the omega is non-zero. So this is a 3 form on P4. So this gives you a vector field. You take this vector field, so omega wedge the omega restricted to the cubic is 0. So this vector field is tangent to the cubic. And you compare the vector field and the one form, and you see that's not possible. It goes like that. You can, yeah, it's easy to classify the shape of these vector fields. It's easy to write down. So we have like 2 cases, and in each of these 2 cases, you see that's not possible to, so that these vector fields come from the restriction of something of the shape of omega wedge the omega. And well, we excluded the three-dimensional quadric, and it's actually known that the space of degree 1 foliations on the quadric has 3 components. You have these 2 components, and also one that's given by an action of the affine linear of the affine Lie algebra, the Lie algebra of the affine group of C. Okay. So for complete intersections, we have a nice picture with some restrictions. The case of hypersurface is like it's complete there, because we know everything. the only case that we couldn't cover is the one that's not possible because it has 3 components. So this case is done. And the next case that we are actually working on right now is the case of degree 2 on quadrics. So if you go back to this, the first general structure theorem that I put there, we see that there are some possibilities to put X as a quadric hypersurface and the foliation of degree 2. Actually, if you look at the inequalities, if you assume that the degree is 2, the only thing that you get is the quadric of Pn, just by Kobayashi-Oshii. So, and in this case, we have the structure theorem that says this either is a closed rational one form with a dimension 1 zeros, algebraically integrable, and admits a subfoliation of codimension 2 and degree 1 for dimension at least 4, f can be a linear pullback, and for dimension 3, this linear pullback is not possible, but it's possible that there's some action, the C or C star action tangent to F. And we are now working on, for instance, if this case, like degree 2 on the quadric is morally the case of degree 3 on P3. There's some, the difficulties are kind of the same. So Jorge, Ruben, and Rafael, they could prove that there are at least 24 components. And the hard part is like to decide where the algebraically integrable foliations fit. So it's not easy to control. And here we have the same problem, like this item, the second item is kind of nasty. We don't know how to approach. And we are now working on this situation, describing the actions on the 3-dimensional quadric. This is quite nice. You have like, so the automorphism of the quadrics are SO5. So, and then you can look at you can fix a Cartan subalgebra of SO5 and do the computation, see what are the possible actions that can happen, and you can like just put this on a computer, and it speeds all the possibilities, and we are checking this. So it should be out soon. And I think that's all I had to say to you today. Thank you.